I'm so excited to welcome Monica Quaintance, who leads engineering adoption strategy at Kadena. She is a former tech lead and senior data engineer at Rent the Runway and a former qualitative analytics engineer at the SEC. She is also the founder of Universal Consensus, a blockchain-focused pro-diversity organization. Monica will be talking about her work here at Kadena.
Thank you for having me. My name is Monica. Thank you for the introduction. And I'm going to talk a little bit about what we're working on at Kadena. We are one of the full-service, full-suite blockchain platforms. This is an Ethereum-type alternative. We like to call ourselves a second-generation blockchain platform. If Bitcoin is a generation 0 blockchain, which means it's a distributed ledger that can take financial transaction records, but it's not particularly scalable and it doesn't allow for any distributed computing, then a first-generation blockchain platform is your Ethereum, which allows for a distributed compute on a blockchain or multiple forms of assets that you can put on a chain, not just money. You can think about other things like a crypto kitty that you can have on a blockchain. But it's not particularly scalable, at least at this point in time. So Kadena, we're trying to position ourselves as a new generation blockchain that allows for your distributed ledger technology with a smart contract application layer on top and is also scalable. So we run Pact, our smart contract language, on top of 2 different kinds of platforms depending on what you're trying to do. Chainweb is for public, which means that if you're looking to do a transaction on a blockchain in which you want to pay other people, strangers, to run your code on some sort of a node, then you can do it on a public platform on our Chainweb technology. If you, as an enterprise, wanted to make your own blockchain, either for internally in your company or for a consortium, for other companies that are known and relatively trusted, although they might be adversarial, then you could use our Scalable BFT consensus protocol. So we have 2 consensus protocols and then 1 smart contract layer that can work on either of them depending on what you're trying to do. Aha, yes. So this is the Kadena for enterprise and Kadena for public. So most of what I focus on in my day-to-day work is on developing what we're calling crypto charters. Everybody in blockchain loves when you come up with a shiny new term. So better than smart contracts, we're calling them crypto charters because a smart contract is not actually a contract. A contract is an agreement between 2 people. And I think that the term smart contract is actually quite poor because what we're doing is we make an agreement and then we want something to enforce it. So instead of a contract, what we have is a charter, which is something that has governance. You agree who's allowed to modify what, and then you put that on the chain. So Pact is smart contracts plus governance, so it's a crypto charter. But that's not the focus of the talk today. I want to talk about our consensus protocol, which is called Chainweb. So Chainweb, we presented at Stanford in January this year. It officially announced our launch of our public project. And Chainweb is a consensus protocol by which you can have many proof-of-work chains, imagine many simultaneous bitcoins, that all reference each other. And the beauty about Chainweb is that each chain can individually create a successful block all at the same time. They don't interfere with each other, and they can all move forward. And they're sort of like in a 3-legged race. They're tied together, but it doesn't mean that each piece can't move forward. They just can't move forward very far until everybody else is caught up. But this allows you to process many, many, many simultaneous transactions, which gives us a degree of scalability that no other proof-of-work project has been able to achieve yet. A serious degree of safety, security, because all of these chains tied together creates a very deep network of proofs. And speed. You can just, once you have a very tight security proof, you can very quickly achieve a transaction depth in your chain that will allow you to pump through many more transactions. So we're going back to the beginning. What is a blockchain? A blockchain is a distributed ledger. This is your very basic original cited in the Bitcoin paper, what is a timestamping algorithm? You stamp a thing, it has a timestamp. You then put another thing that has a hash of that thing in it, which means that you can't change it. It's an immutable record that you append additional information to. So Bitcoin is a blockchain on which you have timestamping, but then you also have this new idea of currency, which you use to provide incentives to the miners to perform computations for you. This idea of a distributed ledger with computation is called proof of work. So why do we call it work? And why do you need proof? So the idea behind a consensus mechanism is that instead of having one person who's in the middle, like imagine a clearinghouse. I want to trade a stock to you. We both put our stock in a central pool. I say I want this much, you say you want this much. Trusted third party does a transaction for us. In theory, a consensus mechanism should allow us to be able to perform this transaction without us having to trust each other. This is the whole magic of blockchain, because it allows us to perform transactions without having to have a trusted third party in the middle. Bitcoin and other proof of work chains do this by making the miners solve a very complicated math problem. They have to brute force the math problem. And by the time you find a solution, by showing that the solution works, you have proven to the network that you are invested in the network and that you did the work, and that therefore your block should be valid. And Bitcoin chooses the longest chain, which is the one that has the valid blocks. So we are a proof of work style project. You may have heard of other projects that are proof of stake. Proof of stake is completely different, and actually our Scalable BFT project is similar to a proof of stake. It involves you proving that you own some share of the network, and you using that investedness can then show that you're not here to just arbitrarily mess things up. That's more like our existing financial system today. Like Goldman Sachs and JP Morgan and Barclays all have an incentive to work together because they have an investment in the network. And proof of stake systems are inherently more like our existing financial system. People have skin in the game. The more skin in the game you have, the more right you have to influence, but that means that there's potential collusion. That means that there's potentially people being able to bribe each other. It takes away the beauty of this trustlessness. That's the foundation behind Kadena. We believe that proof of work inherently means that because the network does not require trust, it is more secure. So this is a blockchain. Regular old traditional proof of work. And the idea is that this graph structure of the network is a single chain. As you create additional blocks, your block height grows, and each block references the previous one. Seems relatively simple. Until you get to Chainweb, and then you start doing things like having many chains, and then having them all talk to each other, which starts to get a little more complicated. But the idea is that we want to have many chains because it provides scalability and security provides speed. So the way that the chains talk to each other is when we generate the Chainweb network, the graph structure is fixed. There's no like make a chain and then fold the chain back in, or like make a fandom chain, or like you own your own chain. Like these are all structures that other projects are doing. We're doing fixed structure of the graph. So at Genesis, we might have, for example, 2 chains. And these 2 chains would each, when you finish a complete block, pass that completed block to your peer chain. And they will include the proof of it in their next header. This way, the chains stay in sync with each other, and they can pass information, but they don't necessarily need to wait for each other. You can get started working on the next one after you've passed your information to the other one. But here's what 2 chains looks like. We had a lot of 2 chains, the rapper jokes when we were developing this paper. I keep threatening to get a poster for the office of 2 chains. So in this one, you have both chains progressing simultaneously, and as they each finish a block, they pass the proof to each other. that doesn't seem that complicated and sort of like, why would it be worth doing? Now imagine it with many more. Each of these graph structures are solutions to the degree diameter problem, which is how you make a graph with the highest order, that's number of nodes, with the minimum number of either diameter, the longest, shortest path between any two nodes, or degree, number of nodes that you actually need to directly reference. The reason we want to keep those things down is degree equals network chattiness. And the reason you want to keep diameter down is I want to be able to propagate information out to the entire network as quickly as possible. So that's why we're looking at solutions to the degree diameter problem. This 20 chains one starts to look a little bit more like the network that we actually want to build. We're probably going to launch our first test net somewhere between 100 and 500, and then keep forking the network upward to greater and greater configurations. All right, so I said some things about many chains creating security. So let's talk about that. So many chains create security because all of these headers referencing each other, in the original Bitcoin paper, Nakamoto goes into what he calls a 51% attack. And this opened the door to many other different kinds of attack analysis that are more sophisticated, but let's start there. And the idea is that if I wanted to buy a car from you and pay you in Bitcoin, then secretly mine my own blocks in which that transaction never happened, and then present it to the network, there might be an ability for me to double spend. I get the car, and then I can go back and erase the transaction in the network. And in the Bitcoin paper, the proof is a little rudimentary, but the idea is that once you wait a certain number of blocks, the probability that anybody would ever actually be able to catch up and double spend becomes incredibly small. Now imagine that instead of getting buried behind 1 block, 2 blocks, 3 blocks, you got buried behind layers. Because the way that information propagates in our graph is that you have 1 block, in the next layer it's referenced by, for example, 3 blocks, and in the next layer it's referenced by 3 times 3 blocks. It begins to grow exponentially the number of references, which really increases the amount of security in the graph. So this is that, which we're calling the Merkel cone, because everybody loves their fun terms. You have Merkel proofs, we have Merkel cones. So this is the idea that propagating information forward becomes incredibly difficult to cheat. This idea of it being difficult to cheat means that we can actually reduce our block confirmation time, because you don't have to get that many layers ahead before it starts getting really, really hard to cheat. That's how we get the speed in addition to the scalability. Cool. So now that we have this fancy graph structure, what are we going to do with it? So we have our smart contract layer, or our crypto charter layer. And then how are we going to actually propagate this information? It uses mining, like every other proof of work project. And the idea is that you want to have many different pools of miners, because let's face it, everybody knows that mining is going to be pooled. But if an individual wanted to replicate only part of the network, you could also do that and consume the very lightweight header stream. So mining groups have an incentive to spread their hash power as widely as they can, because they don't want to have collisions in their own mining. And then if you only wanted to mine a portion of the network, you could do that too. So we're trying to cover as many bases as we can in terms of individual miners and mining pools. So all of these chains that are all talking to each other, they're all going to mine the same currency. And I can have money on many chains or on only one chain. And if I wanted to, I could pay somebody else on a different chain using a cross-chain transfer that's with simple payment verification. It's a destructive transfer in that I first destroy the coins on my own chain, which generates a receipt. I pass that receipt to another chain, they wait for the proof to propagate, and then they can redeem the coins and recreate them. So this way, you never have double the amount of currency in the network. You can have less than, and then have it created again. So the idea is that because you want to be able to have all of these chains functioning independently, I want to be able to asynchronously have this transaction so that I can destroy it on my own chain and generate a receipt at my leisure, and then you can redeem for the coins whenever you feel the need to. I think that limiting the network structure to having synchronous coin transfers would be artificially limiting, and this is actually a benefit to us. I had lots of arguments with other consensus protocol people over whether we should have them synchronous or asynchronous, but in the end, it doesn't really matter. You get the coin from point A to point B. So this is time is going from left to right. First, I will delete the coins and generate a receipt, and then they will move to another chain. So this allows us to not only do money transfer, but will also allow us to do smart contract transfers. So if, for example, I come up with this super awesome new app called Crypto Bunnies, and it becomes super popular on this chain, I can deploy it to another chain by doing a cross-chain transfer, not necessarily a destructive one. I can just propagate it out. Or if the chain that I'm on for some reason gets really clogged and slow because there's some Crypto Bunnies app, I can move all of my stuff off of there and onto another chain. There's no reason that it's not fungible. And since you're waiting n number of blocks, where n is the diameter of the network, for confirmation time anyway, then there's no reason that transferring something from one chain to another is really any slower than doing a transfer on the same chain at the same time. Yeah, so that was a lot of information. It is kind of technical, but I'm happy to answer any questions that you have either now or later. I'll be hanging around. But there are a lot of projects out there and a lot of people doing really awesome math and working on some really cool things. We talk to people all the time that are like, oh, I can't wait to do real estate improvements on your blockchain, or, oh, I've been really thinking about how I want to take my Internet of Things HVAC equipment and put them on a blockchain. So it's a really exciting field. Platform work is at an all-time high. All kinds of people coming up with awesome platforms. I think we have a really good option, especially if you're concerned about things like scalability and security. So come talk to me afterwards. I'm always happy to talk about Kadena. And yes, that's our Telegram group, where we do not talk about any speculative natures about investments, and we only talk about engineering. So come talk about engineering in our Telegram group, and that's my email.
My name's Mariah. Thanks for speaking to us. I had a question for you about forking. I was wondering what would cause you to fork your network, on your network?
So for us, forking is not that big of a deal. We're intending to do forks the way that other networks might choose to do upgrades, but not for upgrading the smart contract language. We would do it for upgrading the size of the network. The only thing, give or take, pretty much the only useful thing that forking the network would do for us is being able to upgrade the network size. And the reason that we think that it's not going to be a big deal is because the people that inherently control forking a network are the miners, because they're the ones actually running the client software. But once the network becomes slow and clogged, the miners are exactly the kind of people that would want to say, yeah, I'll take another 10 chains on which I can generate more money. So we're not that concerned about forking, and that's really the only reason we would do it.
Thank you.
Thanks. I was wondering if you could elaborate a little bit more on smart contracts and your, why smart contracts is not a good term, and why crypto charters that was the term, and why that's important, and what the substance of that is. Thanks.
When non-blockchain people hear the word contract, it means something different in their minds that I think a smart contract actually represents. In the real world, non-blockchain world, a contract is something that two people agree on that can be amended, that can be upgraded, that, we've shaken hands and we've agreed on this thing for now, but it doesn't mean that necessarily that's going to guide us forever. And that sort of relationship is not reflected in a smart contract, which is neither really an agreement, nor is it mutable. A smart contract, as they exist today in, for example, Ethereum land, is, you've already made a decision outside of the network. We've come to an agreement. You wrote that down, and you hope that the code represents the thing that we've agreed upon outside the network, but you can't ever change it, and you can't ever amend it, and you better hope that you didn't make a mistake. Our language, Pact, actually has built into it a governance protocol. And it doesn't have the idea of state. It only has the idea of a rule set. So when you write your pact, what you first create is a multi-key set, and we say, who has the ability to upgrade what? And then on top of that, you have a logic layer. And none of that has any idea of statefulness and can be amended at any time. So that is more like the way a charter governs a company. That at this point in time, these are the people that have the rights to amend the rule set, but that can change when it needs to. We think that that's much more representative of the way that people will want to use what are now called smart contracts, applications on a blockchain, because they should be reflecting actual people's agreements, and then you want to be able to modify your code. One more, because we're almost out of time.
Right. I have a question regarding the blockchain. Since you store the data per chain, it's like pocket type of data. What happens to the whole storage, like storing data for learning in the big picture, like big data, or learning from the whole pattern of behavior of all these buyers or sellers or people who are on the different side, two sides of transactions. I'd like to learn more about the storing part. How do these data store to learn from?
Okay, I'm going to try and rephrase that because I'm not sure if I understood completely, but I'm going to go for it. So the way that we're storing our information is, like Bitcoin, it's a ledger. But you can have a transaction over there, and you can have a transaction over there, and both of those proofs can then be passed to me, and I will accept them and then propagate them forward. I don't necessarily know the transactions that went into those proofs. If I wanted that, then I'd have to actually go to that other chain to retrieve it. But by having their proof, means that if somebody wanted to invalidate one of those transactions, they'd have to invalidate my block as well. So we're not actually passing transaction data from chain to chain. We're only passing the header stream of proofs from chain to chain. So if you wanted to actually go in and analyze like transaction records, you have to do it on a chain-by-chain basis.
Yeah, but the data is stored somewhere.
What data? There's no data. It's a blockchain.
Yeah, I mean, whatever the transaction information is, it's decentralized, right? So
sure.
In this case, big data doesn't mean anything.
Well, if you're replicating chain 1 on your node, then you should have all of the transaction data from chain 1 on your node.
Yeah, for me, as someone who wants to do research on big data, do I have access to those human behavior?
Replicate each individual chain and scrape the transaction record, I guess. Oh. We do have an Oracle link that's built into Pact, so I guess you could just go in there and rip all of the transactions from the smart contract layer into a database.
Thank you.
Thanks. Unfortunately, that's all the time we have, but thank you, Monica. That was amazing.